as far as this one. We actually looked at the entire slide here, so I'm just going to fast forward to the end of it. So we were looking a bit at a solenoid for two-way valve, and how this works, where we, especially for this one which has a detent, if we energize one side, we only need to energize it a little bit, only enough to push the slide over, and then the detent is going to keep it in that position, which means that we don't need to have a constant stream of electrical current going into the solenoid in order to keep it in its position. It's enough to just give it a brief jolt in order to get it moving. The next slide that we're going to look at, we're going to look more into detail at how the detent works. Quite a lot of blackouts here. So we've got the same valve set up here. And when none of the solenoids are being energized, the detent is keeping it in position. And that also applies if you energize both solenoids. So with a mistake, you push both buttons or something so that you send energy into both solenoids. The solenoids are equally strong, so that they will apply the same force to the piston. But since we have the detent keeping it in place, it is also applying some force, which means that since the solenoids are giving the exact same amount of force, it's just going to stay in place because you also have the extra force from the detent holding it there, so it can't be shifted in any direction. And the way the detent works is that we have two grooves. Since this is a two-position valve, we have two grooves, one groove for each position. So if it had been a 4-3-way valve instead, we would have three grooves, one for each switching position. And then we have, basically, it's a ball bearing. So we have balls that are, or orbs that are placed inside the groove there. And they are kept in place by an elastic ring. So this isn't like an elastic that you would put on a paper bag or something to keep it closed. This is more like a plastic ring, but it is able to deform a little bit, which means that in its regular position, it's going to keep the balls into place inside the groove. But if you start pushing on the piston, in this case it would be pushing the piston in that direction, then the groove is going to start exerting some force on the balls in the ball-bearing groove, and it's going to push the balls outwards. So they are going to push against the elastic ring. So it's going to expand the diameter of the elastic ring somewhat. And then as soon as the piston moves enough that the balls are aligned with the next groove, the elastic ring is just going to force the balls back in. So all of the force from the detent is actually coming from that elastic ring for keeping it in place. So that's one way of doing it, having the detent going all the way around the circumference of the shaft there. There are other ways of doing it also, and we're going to look at one a little bit later. So with 4-3-way valves, we have the slide valves, which give us very simple designs. And we have poppet valves that we can use to gain a 4-3-way, basically 4 ports and 3 different switching positions. But it means that we need for an example, 4 individual 2-way poppet valves, and they will be connected to each other. And by controlling which of them is opening, you will gain the same effect as the slide valve does by just moving the slide back and forth. So we can see that using poppet valves as a 4-3-way valve, it's going to be quite more complex than using one slide valve for the same effect. The obvious advantage of using poppet valves is that once they are closed, they are fully closed. There is no leakage past them. So if for some reason in your system you can't allow any leakage past your directional valve, then you will have to design it with poppet valves. But as long as some leakage in the valve isn't a problem, then the slide valve is definitely the way to go. It's cheaper and a lot less things that can go wrong with it, since you only have one valve instead of having four. So with a slide valve, you can have the ability of running a recirculating mid-position, which basically means that when you have it in the center position, you are going to be sending pressure from the pump and straight back to tank. So all of the fluid flow is just going in a circle from the pump to the valve, straight back to the tank, and into the pump again. The way it's been done in this one is that they've actually made the piston slide hollow, and then they have an opening for the pump, the pressure ports, and also for the tank ports, so that once this piston is in the mid location and it's blocking off the pump port, the flow finds the hole in the piston wall, and then it just flows into the slide and through the slide and out on the tank side of it. And that's when you have this kind of mid position in your symbol, where you got the P and T lines connected in the middle. Then you can also have the closed mid position, where you've just blocked off the pressure port, so that it's not going to allow any flow at all. It's a full block off. So when you put this one in the mid position, it's going to create a pressure peak most likely, because you're completely blocking off the flow, and your pump is just going to be sort of pushing on the wall there. And that's the one where we have these different T's on each of the ports. Then it's fully blocked off. As you can see on the top one, we only have the T's on the A and B port, and that's because they have no connection to the other ports in that slide. And here we have a different solution for how to do a detent. So what's been done here is instead of having a groove going all the way around the circumference of the slide, they've just made a cut, basically. So they have 3 cuts in this one. And then they have a hole inside the housing here, where there is a spring that's been locked into place, and the spring is pushing on one ball. And that means that the spring is delivering all of the force to the ball, and when you start pulling or pushing on the slide, it's going to force the ball upwards, compressing the spring. And as soon as you've pushed it in enough for this groove to end up here, then the ball is going to be pushed into place by the spring there. So instead of having this elastic ring going all around, you now just have one steel spring that's in place and just one ball. Yeah, the ball and the spring there. So that's another way of achieving a detent in this one. So for this one, we can also see we have a hand lever. So it's not a push button directly, because you can also pull it. So that's why you have the knob on the end there, so that you can also pull it. So it's more similar to a lever than a push button directly. So this is a manual one with a detent, while the previous one we were looking at, that was a solenoid one. The difference, of course, is that when you have only one spring and one ball that is going to lock it off, it's going to be a lot less force applied than for when you go through the entire circumference of the slide there. So most likely this is a fairly small valve, where you don't need all that much force to keep the piston slide in place. While with the solenoid one, that might have been a really huge valve, so that it needed quite a bit of extra force. We can also put in the transitional positions for 3-way valves. You remember when we looked at 4 2-way valves, where they only had 2 switching positions, we might put in the third box in the middle. So this might be the actual valve itself, but it was also possible to draw in the transitional position, which would be between, for the few milliseconds when you are actually switching between the positions, between this position and that position. It might be, for an example, that it was completely closed, or if you had negative overlap, that you had full flow between all of your ports. So depending on the overlap, you would have a certain transitional position there. You can end up putting in the same in a 4-3 way valve. So now we suddenly have 5 different boxes with positions. But we can see the difference by looking at these two, which have the dashed lines at the top and bottom to show that they're just transitional. You can't keep them there. So that's when the tent has been pushed up and it is moving from one groove to another. So that's when you have these transitional positions. Of course, you could push on in this case, since it's a manual one, you could push it in and not push it all the way and just keep it there, and then you would hold it in the transitional position with your own manual force. Yeah. The spring is nestled inside basically just a drilled hole into the housing of the valve. So it's just it's a blind hole. It's just a hole that goes a little way in, and the spring has just been shoved into there. So that's all that's keeping it into place, basically. That always makes for a bit difficult mounting positions often, because you have to sort of be able to hold the spring and the ball in place while you're sliding the piston slide in there, and then you have to sort of switch places with your finger. So it can be a bit difficult if you're doing manual repairs on one of these that has such a detent like that. But you will also find this design for keeping a position. You will also find that for other mechanical gear also. So you can have it in different mechanical gear that isn't necessarily hydraulic or anything, but where you have something that's going to be able to move back and forth, but it's going to stay in the position when it's been moved. So that once you release it, it's just going to stay there until you move it to the other position. There's quite a lot of different designs for such detents to be used. So in this particular case, we will have full flow from P to A and from B to T. If we push it all the way over there, we will have completely blocked in the mid position, and we're going to have flow from P to B and from A to T over on this side. But when we start moving the slide from this position to the center position, it only blocks off the tank port and the B port first. So I see they've forgotten to put in the T here. There should be a T sign there also. You can see they have both of the T signs on the other one, so I think they've just forgotten it when they created this figure. But it's still allowing flow from the pump and to the A side of the component. So then it gets fully locked into place once you hit the mid position. And then when you move it further to get to this position, you're going to open up flow from the pump and to the B side of the valve, but you are going to keep the return flows locked until you end up in this position, and then it's open and everything. So for an example, if you're operating a piston with this valve, it would be possible for you in this for an example, in this switching position, you would be advancing the cylinder. Then if you're switching over to this one, you will be basically just stopping it. So you could switch to the mid position before the cylinder has advanced fully and reached its end position, and then you can just stop it because you're blocking all ports. So you are locking all of the pressure inside the cylinder. So the pressure on the piston side is locked in, and the pressure on the piston rod side is also locked in. So the piston can't move at all because it's got completely locked in place by the hydraulic pressure there. But what happens while you're switching to this one is that it keeps feeding pressure to the piston side, but it's blocked off the return side. So that is going to basically create a bit more pressure on the piston side than what's going to be on the piston rod side. And the same thing happens when you switch from the closed position and over to retracting your cylinder. You're opening up to the piston rod side, and you are putting more pressure in there before it gets fully opened and you get returned to tank. So you're basically sort of building up pressure before you lock it off or before you open up return to tank. Whether or not that would be useful in your particular situation, that's something that depends on the design and what you are going to accomplish with your cylinder. It might be that you would rather want it to be the other way around, that the pressure and A-port would be locked off, but you would still have flow back to tank while you were switching, so that you could basically just release some of the pressure while you were switching it over to locking it off, so that you wouldn't build up extra. That might be more useful in your situation. You really don't know until you start looking at everything. But all of this has to do with how the overlap has been built up on the different pistons here. So we can see when it's over on this side, I think these are connected to each other, aren't they? Yeah. When we have it all the way over on this side, that means that we have pulled the knob. No, we have pushed the knob in, which means that we have flow from the pressure port. This part of the piston will be moved over there, so we will have flow from the pressure port and to the A port. The T port will be blocked off, and the B port will have access into this area through this over here and then out through the T port, because we have these openings up here and down here, and those go around the piston itself, so that we get flow around the piston here, and then we will get flow over here and then around the piston and out to tank. And all of that will be coming from the B side. So that's when we have pushed the knob all the way in, we're in this position. So when we start pulling on the knob before we get to the mid position, it's going to close off here. So the flow from B over to tank, it's going to be closed off there before it closes the opening between P and A. So that is due to the overlap in it. You have different amounts of overlap on these two pistons. And the same will happen if you continue pulling it outwards. You're going to open up the flow from P to B before you open up the flow from A to T. So it basically means that, just to throw some figures out there, these two pistons, you can see they are quite a bit wider than the middle piston. So they probably have an overlap of, well, maybe 2 millimeters, just to get a fair number here. And then the one in the middle maybe just has 1 millimeter of overlap. So that means that this one opens up twice as fast as this one. So that while you're moving it, you will get a quicker opening and closing of the center piston, but you will have a quicker closing of the pistons on the side. So that's what affects these transitional positions in this case. Yeah, so it's also possible to show those transitional positions, and we use these kinds of cylinders to actuate double-acting. These kinds of valves to actuate double-acting cylinders, and also for motor control, so that we can, by the use of a valve like this, we can extend the piston, we can stop it midway, and we can retract the piston. So it's not a problem doing any of these functions with it. And also for motor control, so we can start the motor running in the clockwise direction. We can stop it by switching over to the mid position, so then no flow gets into the motor or out of it, so it just stops. And then you can run it in the opposite direction, so you're running it anti-clockwise. And I'm going to look a bit more specifically at the solenoid 4-3-way valve. And this one has springs that centers it, so that if you cut off your electrical current going to the solenoids, it's going to place place the valve in the mid position. And in this case, the mid position is fully closed. So we have two working ports, A and B, and we have the pressure port and the tank port, of course, since it is a four-port valve, four-way valve. And in this case, the solenoid is wet, and the DC stands for direct current. So the opposite kind of current from what we have in the wall sockets, that's AC, which is alternating current. And then we have manual overrides on both sides of this one. So it will be possible to have some sort of push button or lever on both sides to activate it should you have a power failure. And then we have the armature, which is the magnetic part of the solenoid, the one that's going to react once you put electric current through the solenoid coil and creating a magnetic field. It's going to interact with the armature and start moving it. And then we have a stem in here. We have spring disc that keeps the spring in place. We have the piston in the middle and the spring itself. So there's a spring on each side and there's also a spring disc on each side. They've just shown them in two different locations. And this one starts getting a fairly complicated symbol. So we've got solenoids on each side, M1 and M2. We've also got springs on each side, and we have push buttons on each side. So we're starting to get quite a lot of information in that one symbol. If we should add the transitional positions also, so that we got 5 squares there, it would be quite a lot of information for one symbol. So in the normal position, the springs are centering the piston, and all of the ports are closed. We can see it here with the T's that are put into place. It hasn't been that bad before with the blackouts, but we'll just have to endure it. That was a bit too far. What did I get? Spring centered, mid position closed. Yeah, for some reason it jumped to the next one. So it's spring centered, and all ports are closed. So then if we energize the M2 solenoid, so we put electrical current in on this side, then we are going to get flow from the pressure port and to the A port. So now the piston has been moved over in this direction. So this spring has been compressed, and this one is free to just stay there. Basically, the spring disc is keeping it in place, so it doesn't follow the piston further on. It just keeps it there. And the position is only retained for as long as we supply electrical energy to M2. So as soon as we let off on the electrical energy, the pistons are going to switch it back into the center position. And then if we energize the M1 solenoid, we're going to slide the pistons over to this side, compressing that spring. And then we get pressure going from the pump and to the B ports. And of course we get return pressure from A to T. It's also opened up. And again, the position is retained for as long as we apply electrical energy. Now, this was the original lecture for Wednesday. We're a bit behind schedule now, but I think we'll catch up as we go on. We were going to become familiar with 3 two-way valves and 4 two-way valves. So we looked at that one and that one. We were going to get to know about the connection between the transitional positions and overlap, how that works. We were going to get to know how the detent works. So we looked at 2 different kinds of detent today, both the one that goes around the entire circumference and the one that's just in one point. And we've recently looked at the 4 three-way valves, so 4 ports and 3 positions. And in this one, we only had the textbook as reference, basically because I couldn't find anything useful on YouTube or as animations. If I had done that, I would have put it in. There is surprisingly little that is of value showing these kinds of valves, so it's a bit. There are some of them, but those are complete lectures with 50 minutes or 2 hours or something like that. So can't show that. I'm supposed to hold a lecture. So then we'll start with what was supposed to be the only presentation for today. So we'll get a little bit in before the break, and we'll see how far we get. There. So for this lecture, we have learning goals of knowing how the mid position influences the function of the valve. So basically, when we're set, if we have a 4-3 way valve, and when we're setting it in the middle position, what influence is that going to have on the function? We're going to become familiar with pilot control of directional control valves. And that is mostly used when the valves are starting to become pretty large and they have quite a lot of flow rate that they can let through them. Because then you start needing a lot more power, actuation force, basically, to move the slide, because the slide is starting to get really big, so you need more force on it. And we're going to become familiar with the pros and cons of direct actuation and piloted actuation. So direct actuation is what we've been looking at right now, so that either the solenoid is directly connected to the piston slide, so that it's moving the piston slide directly, or that we have a lever or a push button or something that we are moving directly, or with a mechanical one where we have some mechanical movement that is directly affecting the stem or the roller on the end of the slide. Whilst the pilot one is actually using pressure in order to move it. So you have a smaller valve, which you are directly actuating, and that one is sending pressure into the larger valve to actuate that one. So that's the point with the piloted actuation. We're going to look more at shut-off valves, so how we can have shut-off valves in our system, which basically just shut down flow. They close off immediately. And we're going to get to know how non-return valves work. They're also called check valves in most instances. And we're going to get to know how piloted non-return valves work, because you can have piloted ones of that one, so those also. So, the influence of the mid-position. So when we had two switching positions, that made it possible for us to advance or retract a cylinder, or run a motor in two directions. But we had to choose either advance or retract, or run the motor clockwise or anti-clockwise. So we couldn't really stop or anything. But that's an option when we have three switching positions, because we can close all ports in the center position. So we can advance, stop midway, continue advancing, and get to the end position. We can retract, maybe stop midway for something again, and then continue retracting it all the way to the end position. So we are free to start and stop as we want while we are moving it. And some systems actually use this quite deliberately, where they have motion sensors or length sensors to see how far the piston rod has been pushed out of the cylinder. And it's at certain intervals it's going to stop, because something else is going to happen, and then it's going to start again once the other stuff is done. So there are quite a lot of systems that use this, but that's especially more in automated production lines and stuff like that, where you can use the same cylinder to achieve several tasks just by having it stop and wait for something else to happen and then continue afterwards. And the same for motors. We can run it clockwise, stop it fully, run it anti-clockwise, stop it fully, and choose how we want it to run. And then we're going to look at three different examples for the mid position. So when we have a 4-3-way valve where the mid position is fully closed, we've got these T's in place, then the piston rod will just look at the piston. It will be more or less the same effect for a motor. So in this case, the piston rod will come to a standstill once we put it in the mid position. Because you're blocking off both the A and B ports, it means that none of the hydraulic fluid that you've pushed into your cylinder can escape from either of the sides of the piston. So that it's fully locked. So even though you go over to the other end of the piston rod and you start pulling or pushing on it, it's not going to move anywhere because you have full pressure on both sides of the piston. So it's going to stay there. And basically the same is going to happen for a motor, because when you are rotating the motor, you're also, if you stand on the outside of the motor and you try to rotate it, the motor will act like a pump. But you have already, you've blocked off the flow, so there's nothing to pump. You can't get anywhere. You won't get your fluid through the motor, so it's going to stay still there also. Then another possibility is to have a recirculating mid-position. So you still have blocked off the ports going to the cylinder or to the motor, so it's still going to come to a complete standstill. But what's now going to happen is that your pump will continue to circulate the fluid. So it's just going to go straight in return to the tank, and that's going to help you get basically more lifetime out of your pump. Because in the previous one, where the pump was also blocked off, the pump will, so long as that will work, so long as it's not going to stay in that position for any length of time. If it's just stopping it, then starting again, stopping it, then starting again, then it's going to be fine with having your pump just pushing at a wall there. But if it's going to stop and then it's going to stay there for 15 minutes before it starts up again, then you really want a recirculating position, because then your pump will be working without any resistance at all. So your pump will just be spinning around, having a great time, and basically not getting any wear and tear from it. While as if you block off the port, like in the previous example, it's going to just keep on pushing and pushing and pushing and basically harming itself if it stays in that position for too long. Then we have another example where we have a 4-3-way valve, and it has a relieving mid-position. So this means that we have blocked off the flow from the pump. So the pump is going to be fighting against the wall, basically. But both of the ports to our cylinder or to our motor are connected to our tank. So that means that if we go over to our piston rod or over to the shaft of our motor, we can start moving it. Because if I move my piston rod back and forth, so if I push it in, then the flow from the piston chamber is just going to go straight back into the tank. And if I pull it out, then whatever fluid is in the piston rod side of the piston rod chamber is also going to be pushed back into the tank. So basically, we can empty the cylinder by pushing it back and forth. We can remove all of the hydraulic fluid in it, if we want to. Wouldn't be smart, because we would end up with air bubbles in the system. So we wouldn't really want to do that. But the piston rod can at least move so that it's free to move. And the same would go for a motor. You could spin it back and forth if you wanted to. So we have 5 different ways of putting up these mid positions. So the second example we looked at was having recirculation between the pump and the tank, and basically just to give the pump a better lifetime. And then we have full blockage, where we just stop everything, which is fair enough if it's for shorter durations. Then you also have one that wasn't a part of the examples, which basically connects everything. So you have the pump pushing in its fluid flow here, but it has the possibility to return straight to tank, so that's not a problem. But you will also have connection up to the cylinder, which means that you can still push your cylinder back and forth, but there is going to be some resistance there because you have fluid being pushed in there. It's basically not much because it's going back there, but you have to really move the fluid. So it's possible to push the piston back and forth, but it's not as easy as in the next one, where they are just connected to the tank and they're not getting any pressure from the pump. The last one wasn't a part of the example, 3 examples either, but for that one, the 2 ports to the cylinder will be connected to the pump. So basically, we'll be pushing with full force on both sides of the piston. And then it basically depends, do you have a piston with a differential ratio? So do you have more surface area on your piston side than on your piston rod side? Then you're going to advance your cylinder. Even though you have full pressure on both sides, the force isn't going to be equal on both sides of the piston. So that is also one way of putting it up. So you're forcing it in one direction, but it's going to be slower because you have more resistance in it. We'll do the next slide after the break. Right, so then we're going to start looking at pilot control of directional control valves. So when we have pilot control, the valve piston is indirectly actuated. This means that we are actuating another valve, and we're telling this valve to actuate the actual directional control valve. So sort of we are placing another step in there in order to get to the original valve. So the main valve will be actuated by fluid pressure through another directly actuated pilot valve. And these are normally solenoid valves, so that the pilot valve is normally a solenoid valve. And it can either have internal or external supply power. I'm going to explain that a bit more as we go along. Because if it's internal, then the pilot valve is built into the same housing as the directional control valve. And by ways of internal pathways, it can open up pressure from the pressure side to get to the slide for the main valve, so that it's going to hit one of the sides of the slide, and then it's going to move it. And same with the tank, so that the opposite side of the slide valve is open to the tank, so that it can push the hydraulic fluid back again. If it is external, then it's going to have extra ports, X and Y ports, and those will be connected to pressure and to tank. So that means that instead of leading the pressure from the pressure ports directly through an internal channel and onto the slide, you're instead gaining pilot pressure from an export, so an additional port, and this one is connected to the slide chambers for moving the slide. We're going to look at it in a figure in a bit, so that it's going to be a bit clearer. Usually we will put in the X and Y ports like this, because this part is the pilot-operated symbol. So this means that the solenoid on this side is going to send a pilot-operated signal to switch over to this position. And the same goes for this side. So the M2 solenoid is going to send the hydraulic pressure into the main valve and switch over to this position. And the Y port will be going back to tank, and the X port is connected to pressure. And then also we have springs here that will center it if you're not actuating the solenoid valves. So if you're not energizing them with electrical current, then it's going to just stay in the mid position. So here we can see how it looks like on the inside. So we have the main valve, that's the lower section here, and then we have the solenoid pilot valve up top here. So we've got the housing for the pilot valve, and then we've got the pilot piston itself. And here we have the pilot line, which is connected to the export. It goes behind the pistons and everything here. It's not in connection with it, so it goes on a different pathway through the housing. It's completely closed off all the way up here, and then it's can be opened up through moving the pilot valve back and forth. On this side, we have a spring chamber with a spring. So these are pretty forceful springs that are able to move the slide back and forth there. And this was the main valve, as I mentioned. We have the spring itself on this side. And this is the main control piston. So this is the one that we are going to activate with use of the pressure energy that comes through the export and up here. So we are going to be able to send this pressure either to this side or down on this side to actuate the main piston. We also have a spring on this side, and we have a spring chamber also on this side. So I think in the textbook it says right-hand spring chamber and left-hand spring chamber. I'm going to show it more in detail than what the book does, so that I'm not going to put in the names here. So if we have it in the neutral position, this is how it looks. So we have none of the solenoids have any energy coming in, so that they are not activating the pilot valve, and it is blocking off all flow from the export, so that there is no pressure energy coming in that way. Which also means that the springs are the only thing that's acting on the main control piston, and they're just keeping it in place. Yeah, the springs keep the valves in neutral position, and all the flow from X is blocked. So then if we energize the M2 solenoid up here, then the pilot piston is going to move left, and the left-hand spring chamber is going to be actuated. So now the piston has moved a little bit left, and we are getting flow from the export up here and down into this spring chamber. This means that the main piston here is going to move to the right. And it's going to open up flow from the pressure port to the A port, and also from the B port past the piston up here and down into the tank. Then if we de-energize the M2 solenoid, so we release the electric current going to it, then everything is going to be moving back into the neutral position. And we can see that the pressure that we gained here, which was coming from the export, that has now gotten an opening back to the Y port, and it's going back to tank. So it's being just forced back into the tank instead. So then if we energize the M1 side, so this solenoid, the pilot piston is going to move to the left, so over here, no, to the right, and then we are getting pressure from the export up here, and it's going down into this spring chamber. And the main piston is then going to move to the left, as we'll see, and we get flow from the pressure port and to the B port, and we get return from the A port and directly to tank. So if we stop supplying electrical energy to M1, then we return back to the neutral position, and all of the fluid that we had in this spring chamber is going to be pushed back across this extra channel up here and then down into the Y port and into the tank. So it's a pretty roundabout way of doing this, but it's a lot better than trying to put these solenoids directly on this piston, because as you can see, the piston here is quite a bit smaller than what this one is. So this one has a lot of inertia and mass, so just moving it back and forth is going to require a lot of energy, which means that we would have to ramp up the size of these coils for the solenoids. And that would mean that we would have a much bigger valve. So by doing it in this way, we get to use smaller coils, and we still achieve the same function. And the total size of the valve becomes a bit smaller. So not just a little bit, but quite a bit smaller. So now we're going to compare a bit, having a piloted directional valve and one that we directly actuate, so the first kind we were looking at. So if we have the direct one and the piloted one, we look at both of those and the amount of actuation force they need. It's going to impact the size of the valve. So for a smaller valve, it's okay to use the direct actuation method, because you don't need so much force, which means that the solenoid part is going to be fairly small. But for the piloted one, we do need to use a lot of force, and then it is better to use the hydraulic pressure, which we already have in our system, and just direct it to actuate the valve instead. Because then we can still use the same size of solenoid coil on our valve, but we can operate a much larger valve with it. So the direct actuation is very ineffective when the valve reaches a certain size due to having to have the solenoids much larger, or if you were going to try to do it manually, you would have quite a lot of problems moving the lever in it. And the pilot actuation, we use those for larger valves to control large amounts of hydraulic powers. And the directly ones take up less space, so if we can, we would choose to have a directly operated valve, seeing as it's both cheaper and takes less space in your system. But still, if you have a large enough force, you're not going to be able to do it with a directly actuated one. So then we're going to start looking at shut-off valves in Chapter 9. And I actually think we might be able to catch up today for us get to the end of this one. The shut-off valves are designed to block flow in one direction. So they're going to allow free flow in the other direction, but if you try to switch it around, then it's just going to stop and close off everything. And shut-off valves, they have to be leak-free, so they are always designed as poppet valves, because we really don't want any leaks going past the shut-off valve. So they use a sealing element, so a ball or a cone, which is pressed against a corresponding seat. So basically a circular opening, and then you have a ball or a cone that is pressed into the circular opening. That's going to create a complete seal in that opening, so you won't be able to get any fluid going past it. So the volumetric flow in the flow direction is able to open up the valve by basically just pushing on the ball or on the cone. It's pushing on the ball or cone, and then it's pushing it up, so it opens up and is able to flow past it. But in the other direction, it is pushing the ball or cone into the seat, so it's basically just making it shut even more if you're trying to get flow in the other direction. So we have two types of them. We have regular non-return valves, which are either load-free or spring-loaded. We're going to look at the spring-loaded types, which are the most common ones. And we also have lockable and piloted non-return valves, where we're going to look at the piloted ones. So lockable just basically means that you can close it off completely so that it's not going to deliver flow in any direction, if you want to. And you can also lock it in the open direction so that it's going to allow flow in both. So for this figure, they're using a cone element to close off and gain sealing with a compression spring behind it. And we have the sealing cone itself there. And if we look at the cross-section exactly where the sealing cone is touching the circular opening, we get a disc shape. So just by looking at the cross-section there. And that's the area that any flow coming from this side, pushing on the cone, it's going to affect this area. So then we get pressure, we multiply it with area, and we're going to get force. And once that force exceeds the force on the other side of the cone, it's going to open up, and then you get flow through it. But if we get just flow from this side, it's fully disabled, because then we have both the spring and the pressure P2 here. That's all of it is pushing on the cone, and it's just making it seal even more, basically, so sitting even tighter into the opening there. And once we get flow from the other direction, the pressure of P1 needs to be greater than P2 and the spring in order for it to open. And this is the typical symbol that's used for a check valve or a non-return valve. So it's even though it's a cone that's being used inside it, the symbol usually always shows a ball instead. So, but you get the same effect whether it's a ball or a cone. It doesn't really matter. So if the valve has no spring here, so if it's just lying loosely inside the area here, flow from this side will still press it into the opening, but then it's only the flow from this side that's counteracting the P1 pressure. If it has no spring, it's definitely not going to be a cone. Then it's going to be a ball that can move around inside there. And that's a regular one for very cheap uses. Then you will have just a ball lying in there for it. And then all you need to do is to get a pressure of P1 that is larger than your P2, and you're going to open it up without a problem. But so long as we have a spring mounted inside our check valve, the P1 pressure needs to be greater than the P2 pressure of this flow, but also the PF, which is the force of the spring, basically. So PF there is the spring force, and PF equals to the force of the spring and divided by the area of the disk that we are subjecting it to. So because with the spring, we're not getting a particular pressure from the spring, we're getting a force because it's pushing with a certain amount of force. But we are, with regards to flow from this side, we are dividing all of that force across the disk section, cross-section that we have there. So that's why we set up this one in order to get the PF there. Yeah, so that's the disk there. That being said, as I mentioned there, if we don't have a spring, it's usually a ball that's just floating around in there, and once you get flow going this way, the ball will sooner or later, very quickly, be placed in front of the opening by the flow, and then it's going to block it off. But there is also one other way of doing this, which is this kind of valve, which is in use quite a lot in pharmaceuticals and stuff like that, because they can create it from different kinds of materials than spring steel. And that means that they can avoid having the spring steel in contact with whatever is flowing past it. So if you have something biological that you are sending past this check valve and you want to keep it free of contamination, you need to have certain kinds of materials in your pipes and also in your valves. And in this case, I think they're using some kind of surgical steel or something that they've been using, but that's not really good for using as a spring. It doesn't have the correct compression properties. So what they're using here instead is actually magnets. So this is a magnetic check valve. So they are gaining spring force by using magnets. So basically just like a solenoid, they can send a magnetical field through this one, which is going to push it towards the opening there. And then the flow coming from this side, it has to overcome the magnetic field and also the pressure on the other side, if there is any pressure there. So it's another way of sort of bypassing the whole spring problem, is actually using magnets. But I'm fairly certain that these are very expensive. I don't think they're really cheap to use. So, but that was one of the main areas where they were using these, is in pharmaceutical stuff, where they have very high requirements to what they can use. So it was just nice thing to throw in there, just to see that even though we're working with hydraulics, we are actually using the same principles in quite a lot of other fields. So just if you're donating blood in the hospital, they are basically using hydraulic principles to handle your blood and everything. So it's you use these principles in many more locations than just hydraulics. So we're going to look at a couple of examples of how to use non-return valves. So in this case, we have a cylinder which is pointed upwards, and it has a mass on top of there. So that means that once we've extended our cylinder, we have a certain amount of gravitational force that is pushing on the cylinder in order to push it back. Which means that we're going to have to look into what kinds of valves we are going to use in order to avoid the cylinder sliding back once we stop flow into it. So one way of doing it is having a shut-off valve that is effective in just one direction. So in this case, we have we have a directional control valve, which we can open and close. And we have this throttling valve to limit our flow. So this part of the valve throttles our flow to a certain flow rate, which means that we can regulate the speed at which we are extending our cylinder. So as long as we are activating this one, we are gaining pressure from our pump. It's going through the throttle valve and into the piston chamber, and we are extending the cylinder. So we are pushing the mass upwards. And it's going to pass through the check valve also, so we are going to get a certain full flow through here. But once we shut off the pump here, so if we still keep this one activated, so that we actuate it and it's connecting the P port and the A port, but we shut down our pump. So we might have a power failure or something, so our pump is shut down. Then the mass up here is going to start pushing on, well, it's not going to start pushing, it's always pushing on the cylinder, but it's going to start have an effect because now we are not supplying hydraulic pressure to the cylinder anymore. So it's going to start moving the cylinder, the piston downwards, and it's going to be pushing flow down here, and the flow is going to get to the throttle valve, and depending on what settings you have on it, if you've got the throttle almost all the way to zero, so that it's just barely allowing some liquid to pass through it, then it's just barely going to allow a little trickle of flow through here, while the check valve stops it completely, so that it won't be able to bypass the throttle valve at all. It has to go through the throttle valve. And usually with throttle valves, depending on the range of flow rates it works in, but very many of them starts at zero, so that you can shut them off completely if you want to. So you can just keep turning on the knob until you hit the end, and then there's going to be no flow through it. So even though you have a little bit of flow open there, you will get flow back here, and it will go back to your pump. So it won't return directly to tank, it will go to your pump. But then you can get the pump to just rotate slowly. So you're not going to harm the pump in any way by allowing that. Do you have a question? Yes? The throttle point, yeah? Yeah? Yeah, it does block it. So it acts. The principle is the same as the choke valves in subsea production systems, where you are basically just changing the cross section of the flow there, so that you are throttling down the flow, and you're creating a smaller cross section. So the velocity is going to increase, but you're also getting quite a lot less fluid past it. So you're basically just creating a smaller and smaller cross section, and many throttle valves you can just close it off completely if you want to. But the thing is, if you're pumping pressure through from the pressure ports, so if you're getting pressure up here, then it's going to bypass the throttle valve and be able to pass through the check valve, so that you can, if you open your throttle valve fully and considering also the check valve there, you can get full flow up in there to extend your piston. But when you're going to release it back down again, the check valve is going to stop completely flow through the bypass part here, and then it's only possible to have flow through the throttle valve, where you can regulate your flow. Then we have one other way of doing this. So if we disregard this part of the diagram right now, so another way of doing this is to have the second setup here, where we have a bypass of a pressure relief valve. So here we have pressure coming in this way from the cylinder. It's going to hit the check valve and just stop, so it's not getting anywhere there. But if we get too high of a pressure here, so that if suddenly someone piles on even more load on top of this cylinder, so that the mass increases and we get more force working up here, then the pilot pressure here can activate the pressure relief and open it up so that we get a flow back to tank, and that's going to allow the cylinder to descend again or retract itself. But the point with this check valve here is that if we get too much force, so too much pressure going through this one, we can possibly harm the return filter if we have that, or you can't always have too high of a pressure in your return lines and everything. So it actually allows flow to some of the pressure to go back in here to this side. So it sort of opens up and makes sure that you get more equalization of your pressures there. So that's one way of using non-return valves. Then we also have a third one, which is to protect the pump itself. So now first off, we'll just look at the middle part here and just think that we're basically just sending it directly into the cylinder. We're going to look at everything afterwards. But for pump protection, we can have a check valve working here. So when the pump starts working, it sends the flow past the check valve. It's going to open up. But if you shut off the pump and you get a lot of force going here, it's going to just block off the check valve. Which means that the load pressure here, it can't hit our pump at all. So it's not going to touch our pump in this number 3 case at all. That was quite a lot now. So it also means that if we get any pressure peaks in our system, so let's say that this cylinder is actually pushing on a lift or something. It's a short lift going up just a half a floor or something, just to lift trolleys and stuff between one half floor and another. And if someone is standing on top of this lift then and they are jumping up and down, they're going to create quite a lot of force. So they're going to create pressure peaks every time they land on the elevator. It's going to push even more on the elevator. So we're going to get quite a lot of pressure peaks on this side. And the pressure peaks, even though we are pumping from the pump, the pressure peaks are just going to block off the non-return valve every now and then. So each time a pressure peaks opens up, it's going to block it off, and then the pump is just pushing against the non-return valve, not really getting anywhere, until the pressure from the pressure peak is dissipated through this valve, the pressure relief valve. Then the pump can start opening the non-return valve again and let the flow return back into the cylinder. So as pump protection, it can both protect against the load itself, so if you just have a static load that's just pushing on the cylinder, but also if you're creating pressure peaks inside your system. So it's going to protect your pump against it. And if we look at the entire system as a whole right now, we can have our pump running, just pushing full flow into the cylinder, extending it. If we get too much pressure, we're going to open up the pressure relief valve so that it's going to open return to tank until we have equalized our pressure again. If we get too much pressure in our tank area, then this check valve is going to open up and allow it to bypass back into the system so that we get it equalized. And if we want to return this one, because now we have a pump that's working continuously, always pushing our flow into the cylinder. So if we wanted to return, we have the possibility of opening up our throttle valve to the set flow rate that we wanted to, and then we can actuate this valve. We're going to open it up, returning to tank here, and then we get flow through the throttle valve. And again, if we are actuating this one, we're getting flow through the throttle valve and down to our tank. Then we can, if we get too much pressure going through this one, so that we get back pressure in our tank system, and the check valve there opens up, to allow the pressure to equalize, then the same thing is going to happen here, because we're still going to get the same pressure up through the tank here, and then this check valve will also open up and allow it back into the system. So then we're going to look at the piloted non-return valves and how they work. So just like with the regular non-return valve, we are blocking flow from B side to the A side on this one. So from one side to the other, the flow gets blocked by, in this case, the ball element that's lying in there. And if we run flow from the A side, then we are opening up the ball element, and we are getting it into the B side of our valve. Because the pressure of the flow on the A side is just going to push the ball element away from the opening. But we can, by applying pilot pressure through the export here, so we can apply pressure here that's going to push on this piston, and it's going to hit the ball element and open it up. And that's going to allow us to have flow from B to A instead. One of those piloted valves look like this, where you have the regular check valve symbol with a spring in it, but you also have the pilot line going into it. So this means when we get pressure going through our export here, it's going to hit the ball valve and it's going to push it open so that we allow flow from B to A. And if we don't have any pressure on the export, the only way that we are going to get flow through this one is from A to B, because that's the only thing that's going to be able to open up the non-return valve. Yeah? Yeah, if you are pressurizing the export here, and you get a higher pressure coming from A, then it's going that way. But it would have gone that way anyway. Even though you didn't pressurize X, flow from A to B would happen like up here. Because that's how this valve works. Flow from A to B will always be free, so it will always open up if we have flow that way. But the only way that you can get flow from B to A is by activating the pilot pressure. So long as you don't have any pilot pressure, it is completely impossible to get flow from B to A. Well, not completely impossible, but if you do get flow from B to A, then the valve is broken. so you can't use it anymore. So then we're going to look a bit at ways of using systems like this. Again, we have the cylinder that is pointed vertically and getting a load on it. So it has a mass pushing on it. So we have the double-acting cylinder up here. So this time it's a double-acting cylinder. Last time it was a single-acting cylinder. It only had a port coming into the piston chamber. Now it has ports on both sides of the piston. And it is controlled by a 4 two-way valve. So we have 4 ports and we have 2 switching positions on it. And you can see the A port is going up to the piston chamber, and the B port is going up to the piston rod chamber of the cylinder. We also have, between the A port of our directional control valve and the piston chamber, we have this piloted non-return valve in place. So if we send flow from P to A, it's going to go up to the piloted non-return valve, and it's going to pass straight through it because it's going to open up the non-return valve, and it's going to fill in the piston rod chamber. But in order for us to be able to switch to this position and have flow from P to B going up into the piston rod chamber and basically retracting the piston, we also need to have flow going from the piston chamber and past the non-return valve. And the only way for us to be able to do that is to activate the 3 two-way valve that we have over here. Because the 3 two-way valve is going to activate the pilot pressure that's going to open up the non-return valve. So this means that when we actuate this one, So we are switching it over to this position. We will get flow, we will extend our cylinder, and we will reach the end position sooner or later. So then we stop actuating it. It will switch back to this position, and it's going to try to push the piston back, but it's not going to work because the flow is stopping. So the return flow from the piston chamber is just stopping at the non-return valve. So the only way that you can make it return is to actuate the 3-2-way valve. So then you switch it over to this position, you get flow from the pump into the P port, over to the A port, and into the X port of the non-return valve, which is going to push on the ball element inside there and open it up so that we get flow in return here. This could have been solved in another way by using a 4-3-way valve here with a closed center position, for an example, so that once you put it in the center position, it would close off all ports. Then you wouldn't have any flow from the cylinder at all. But this is just one way of solving. There are many ways of solving a system like this, where you can try to keep the cylinder in place. The good thing about this one is that you have absolutely no leakage past the non-return valve. If you used a 4-3-way valve here with blocked ports in the central position, you would have leakage between your ports, because that's just the way slide valves work. So here, the cylinder will be locked into place. There is no way for it to move unless we are actuating the non-return, the pilot pressure on the non-return valve. One other way of doing it is by actually using a 4-3-way valve. So instead of having two different valves to operate it, so one to operate the cylinder itself and one to pilot the non-return valve, you might put it in a 4-3-way valve and run everything from one valve here. So we still have the double acting cylinder, and we now have a 4-3-way directional control valve there. And we have the piloted non-return valve still. But now it's connected, the pilot line is connected to the piston rod chamber and the B port there. So unless we are actuating this one and switching to this position, we won't get any pressure on the X side there, on the X port. Yeah, that was what I just said. One thing that can happen here is that if something a little bit remarkable in this situation happens, and something actually starts pulling on a piston instead, so that it's pulling it and it's creating pressure on the piston rod side that is going back through the side here, but it's hitting the blocked port there, so it can't really escape. Then you're suddenly building up pressure, and you're going to open up your pilot operated non-return valve. In such situations, you might actually end up with the non-return valve being blocked in an open position, because you can't get rid of the pilot pressure at all, so it's going to just stay open. So they're not that good to use if you have fully blocked ports in the mid position. So it would be better to switch and have both of the ports return to tank, because then you're going to relieve all pressure in here, and all pressure from the A port down here, and all pressure from the piston rod chamber and the pilot ports all the way down to tank. So the only place you're going to have pressure left in your system is between the non-return valve and the piston itself inside there. So it's a bit better way of designing the system by choosing that. Then we just made it today. So we were going to know how the mid position influences the function of the valve. So we looked a bit at that with the 5 different options for the mid position, blocking it off completely or having free flow between all of the ports, or just having flow between a couple of the ports. We also looked at pilot control when we have directional control valves, where we have the pilot valve up top and the main valve below. And we also looked at advantages and disadvantages of pilot control and direct actuation of the main valve. And we became a little bit familiar with shut-off valves to begin with, and then we looked more into detail on how non-return valves work and on how the piloted non-return valves work. So then we're done for the day. This is actually the data sheet for that magnetic valve. So if anyone wants to look a bit more at it, they can look at the link there and have a look. Have a good weekend, everyone.